At an observatory in California, a solar physicist prepares his equipment for daily observation of the sun. Near Brussels, Belgium, a scientist adjusts the automatic controls which keep his telescope focused on the sun to observe solar eruptions. On a naval vessel in the South Pacific, astronomers prepare to receive data from rock. Since time began on Earth, each turn of our globe has brought the sun again into the east, radiating the warmth and light of a new day. The sun carry with them the energy which makes all life possible on this planet. Even below the surface of the sea, life exists only with the help of the sun's energy. The myriads of microscopic plants in the sea depend on sunlight. These plants provide food for larger creatures. Thus, the cycle of life is carried on. It is the sun's energy which lifts water from the oceans into the atmosphere to form clouds and carry on the Earth's water cycle. Winds, much of whose energy also comes from the sun, blow the clouds and their burden of water across the land, spreading their precious gift of rain. Green plants harness the energy of sunlight, which makes possible the miracle of photosynthesis. In this process, plants convert billions of tons of carbon dioxide, restoring much of the oxygen we breathe.
The importance of the sun to life was sensed even by ancient man, and so he worshipped it. The early Egyptians believed that the sun god, seated in a barge, sailed up the heavens over the back of the sky goddess in the morning and down into the arms of the god of the underworld in the evening. In Greek mythology, Helios, god of the sun, was reborn each day to drive his chariot across the skies. The Aztecs offered human sacrifices to the sun to solicit its continued blessings. Gradually, from a symbol to be worshipped, the sun became an object of intensive scientific study. During the 16th and 17th centuries, astronomers evolved new and revolutionary theories upon which today's astronomy is based. Copernicus, a Polish astronomer, explained that the Earth rotates around the sun instead of the reverse. Galileo, the Italian, first recognized that sunspots were actually on the surface of the sun. From their movement, he concluded that the sun rotates on its axis. Early telescopes were primary tools in developing and expanding this new knowledge.
Today, astronomers continue to expand this knowledge with the help of instruments of greater power, precision, and variety. They not only watch the sun, they measure it. They analyze its structure and the complex forces behind its brilliant glare. The sun is 93 million miles from the Earth, yet it is our nearest star. The next nearest is more than 200,000 times farther away. In his search for wider knowledge of the star-studded universe, the astronomer must concentrate upon the only star whose surface he can see, the sun. Like the Earth, the Sun is a sphere, spinning on a tipped axis. Its diameter is 100 times that of the Earth. Its volume is 1,000,000 times greater, yet it is only an average star. It is dwarfed by myriads of others. If you magnify a section of the Sun's vast surface, it appears mottled or granulated. The Sun is neither solid nor liquid, but a mass of brilliant hot gases, with temperatures varying from 9,000 to about 30 million degrees. Deep within this vast inferno, fantastic energy is generated by nuclear fusion. Great emissions are spewed into space. Among these emissions are particles, bits of atoms torn apart in the Sun's great furnace and ejected sporadically in broad streams. When these approach the Earth, they come under the influence of its magnetic field and are drawn in toward the magnetic poles. In addition to particles, the Sun emits a broad range of electromagnetic wave radiations, which reach the Earth in less than 9 minutes. These include the light we see. If ordinary sunlight is passed through a prism, it splits up into the colors of the rainbow. Each color has its own wavelength. But these visible rays are only a part of the whole range or spectrum of the Sun's radiations. Just beyond visible light are ultraviolet waves. Most of these are absorbed in our upper atmosphere, but some get through to give us our suntan. Even shorter in wavelength are X-rays. These dangerous emissions are also absorbed in the atmosphere. At the other end of the spectrum, among the longer wave radiations, fall infrared rays, which we sense as heat. Last come the waves which lie in the radio frequency part of the spectrum. The whole spectrum of solar radiation is the astronomer's richest source of information about the Sun. Each of the many hot gases of the Sun gives off radiations at specific wavelengths, as unmistakable as a fingerprint. These show up as fixed lines on a solar spectrum. The astronomer can identify the elements present and draw important conclusions about their temperatures, pressures, motions, and magnetic state. Instead of looking at the solar spectrum as a whole, the astronomer can study the Sun in the light or wavelength of a single element, such as hydrogen, calcium, and helium. With each element, he can study different kinds of activity in the Sun's atmosphere at different levels. Here, the Sun's image is passed slowly across a narrow slit. The beam of light is filtered below so that only a wavelength of one element reaches a photographic plate. A complete picture of the Sun can be built up in this one wavelength. Here, one of hydrogen. The Sun in the light of hydrogen, its most abundant element, shows the tremendous forces constantly at play in its atmosphere. Solar astronomy is not entirely earthbound. Cameras have been developed which can be lifted by balloon well above the distorting effects of the Earth's atmosphere. At a height of over 80,000 feet, this camera photographs the Sun once a second for several hours. The camera telescope returns to the ground by parachute. The photos, the clearest ever made of the sun's surface, reveal unsuspected details which give new clues to heating processes deep within the sun. To study radiations which are absorbed far higher than balloons can climb, research rockets are sent up 50 to 200 miles. Taken from a rocket, this photograph in an ultraviolet wavelength shows bright areas of hot gas clouds in the solar atmosphere. The dark areas are cooler gases. Ship-based rockets have also been used to study radiations during an eclipse in the South Pacific. Rockets were sent up before, during, and after the eclipse. Just before the moon hides the sun, the first rocket reports X-ray and ultraviolet radiation as usual. But when the eclipse becomes total, another rocket reports X-rays only. With the moon passing on, exposing the sun's disk again, a last rocket is launched. Now, ultraviolet is detected again. Some solar physicists therefore conclude that X-rays may be emitted by the sun's corona as well as the surface, while ultraviolet comes from the sun's surface only. In piecing together the complex story of the sun, few of the many invisible radiations have provided the scientists with more telling information than solar radio waves. Optical telescopes focus sunlight by means of mirrors and transmit it to an eyepiece or photographic plate. A radio telescope focuses solar radio waves and carries their impulses to a receiver which records them and makes them audible. Solar emissions in the radio wavelengths vary with the level of activity on the sun. Sudden increases in activity may intensify the radio noise from the sun many thousands of times within a matter of minutes. A single radio telescope gives only generalized indications of solar activity, but used in combination, these telescopes permit radio astronomers to observe remarkable detail and to localize specific regions of activity. We have come a long way since Galileo. Today, we distinguish the sun's radiations. We reach beyond the Earth's atmosphere to observe the sun from outer space. We hear the sun through its own radio signals. Yet the same sunspots that intrigued Galileo still intrigue us. In their strange patterns may lie answers to many mysteries. Sunspots appear as irregular blotches on the face of the sun. They seem dark only because the surrounding area is so bright. One sunspot may cover hundreds of millions of square miles. Here, a giant spot dwarfs a circle the size of our Earth. Since Galileo's time, astronomers have observed sunspots almost continuously, counting them, mapping them, noting their movement. These photographs, taken on 11 successive days, show the movement of the spots across the face of the sun. By keeping a careful check on the number and location of sunspots, astronomers discovered that they follow a regular cycle.
The cycle begins with the appearance of a few spots in the medium northern and southern latitudes of the sun. In time, more spots appear, closer and closer to the sun's equator. Later still, the spots decrease until few or none remain. From beginning to end, this cycle averages about 11 years. Close examination of a giant sunspot reveals its complex structure. Strong magnetic fields are known to be involved. The nature of these fields is not fully understood. Sunspots usually appear in pairs, and it has been noticed that one of them has a positive magnetic pole while the other is negative. As if a horseshoe magnet were buried in the sun.
For centuries, astronomers concentrated on the surface of the sun. Only rarely, an eclipse revealed the sun's high atmosphere for a brief moment of study. But today, the astronomer has developed an instrument called the coronagraph, which can create an artificial eclipse. With the coronagraph, the scientist can mask the light of the sun's blazing disk and expose the corona. If all the light except that of hydrogen is filtered out, the halo of the corona disappears. Great hydrogen prominences then become visible. Fantastic clouds of hot, thin gas with temperatures of about 30,000 degrees move in violent unrest above the sun's surface. Time-lapse films show these prominences reaching hundreds of thousands of miles into space, moving at speeds up to several hundred miles a second. Their arches and loops, the manner in which they seem to be pulled back into the sun, suggest that the prominences are controlled by magnetic fields. Sometimes the observer catches a sudden, particularly brilliant eruption called a flare, which occurs in a few minutes, like the bright spot here, and then dies down in an hour or less. Seen against the sun's disk, a flare may light 50 million square miles of the sun's surface to several times its normal brilliance in hydrogen light. Flares occur low in the sun's atmosphere, usually above a sunspot. The sunspot's magnetic field changes abruptly at the time of the flare, involving enormous energy changes. Both particles and wave radiations are emitted. The radiations, which reach the Earth in 8.5 minutes, bring to our optical and radio telescopes the visible and audible evidence of a flare. In addition, ultraviolet and perhaps X-rays cause our own radio communications on Earth to fade out. 20 to 40 hours behind the radiations, particles emitted by the flare reach the Earth and spiral in toward the magnetic poles. Here they interact in a complex way with molecules in the Earth's atmosphere. The atmosphere then glows like gas in a neon tube, creating the aurora, the northern or southern lights. These shimmering draperies in the night sky, greatly speeded up here in time-lapse film, occur at heights ranging from 60 to 500 miles. At the same time, the particles cause radio blackouts. Normally, our shortwave radio signals are reflected by electrified layers in the atmosphere called the ionosphere, 50 to 350 miles above the Earth. But after flares occur, solar particles may alter the electrical properties of the ionosphere, which then no longer reflects radio signals. Because the effects of a flare are so varied and important, not only to science but to routine communications, a special warning system has been set up near Washington, D.C. to coordinate worldwide observations. A message comes in from a European observatory reporting a major flare. The system goes into high gear to alert observatories all over the globe.
Hello, European observatories have just reported a Class 2 flare now in progress at 290 degrees heliocentric.
Okay. This is KA2XAM Boulder calling KK2XEY, Sacramento Peak, New Mexico. We just have a telephone report from the Bureau of Standards, and they report a Class 2 flare was seen from a European observatory, which is now in progress at 290 degrees heliocentric. 290 degrees heliocentric. And I hope you will be able to get a look at it. Did you read me? Over. Class 2 flare is now in progress. 290 degrees heliocentric. Over. Yes, Alice, that is correct.
Observers everywhere begin to submit reports. From a flying cosmic ray laboratory off San Diego.
Neutron monitor operated normally on latitude run from 35 north to equator and return along 120 west longitude meridian. Altitude constant at 30,000 feet.
From the Department of Physics of the University of Minnesota.
Cosmic ray beta balloon number 39 launched successfully at 2116 GCT, carrying both Geiger counter B assembly and emulsion pack 20. Reached altitude 85,000 feet in 2 hours, 45 minutes, and remained for 16 hours. Apparent increase in counting rate about 0230 GCT. Radar tracking successful and telemetered signals clear.
From the Philippine National Observatory in Baguio.
Optical patrol maintained from 2200 to 0415 Greenwich time with several interruptions due to clouds. Solar flare observed in progress at
From Tokyo Astronomical Observatory at Mitaka.
Radio patrol of Sun continuous from 2030 Greenwich until sunset at 0845. Frequencies 50 megacycles, 200 megacycles, 600 megacycles in both left and right hand polarization. Flux enhancement at 2310, lasting for rest of day.
From Radio Research Laboratories, Sydney, Australia.
Solar radio bursts observed with radio spectrograph as follows. Type 1 at 0014, Type 3 at 0225, ranging from 1 meter wavelength to 7. Very strong intensity.
From Crimean Astrophysical Observatory, Partizanskaya, USSR.
Optical patrol started at sunup. Observed flare just ending. Importance 1 or 2. Location north 14 degrees, east 33 degrees. several sub-flares in same sunspot region. Eruptive prominence at east limb position and...
Thus the scientists cast their global net, hoping to snare a few more facts. Facts which may help overcome costly communications blackouts. Facts which may tell the meteorologist how upper atmosphere events are related to the weather. Facts which may shed light in a dozen other fields. New methods, unprecedented cooperation, intensified observations, all speed up the rate at which the sun's mysteries yield to science. But this great body of heaving, furious gases, 93 million miles away in space, still hides many secrets. Secrets of the nature of the universe, perhaps of life itself. Secrets that may one day be revealed through greater knowledge of our nearest star.